So it's my great pleasure to introduce James Maynard, Oxford University, who's going to be the first of a double act on large values of Dirichlet polynomials.
Okay, great. Thanks a lot, Andy. So thanks a lot for the organizers for inviting me to speak here at this conference. It's a great pleasure. Although I haven't worked so much directly with Peter, I still feel that Peter's had a very strong influence on my mathematics. In the language of Freeman Dyson, if mathematicians are birds and frogs, I'm definitely a frog, but it's the influence of people like Peter that mean that I'm a frog who sometimes goes to bed at night dreaming of what life might be if I was a bird. And so I feel that Peter's always great at encouraging me to try and think about the bigger picture and how analytic number theory fits into the wider context. So I'm very grateful. And it's only a big pleasure to talk about this question about large values of Dirichlet polynomials, which is a topic that's close to my heart. So as Andy mentioned, this is going to be a double act. So I'll be the first course. Larry will be the second course, and everything that I'm going to say is joint with Larry. And the hope, from my point of view, for this talk is that I'll give a general overview of what our result is, how it fits into the context, and some of the general ideas from the proof. And then Larry will maybe give a slightly digested form where he goes into some of the details, but also gives his own take on things. So hopefully, even if you hate my talk, then you'll much prefer Larry's talk, and you'll get a different understanding from that. So maybe I'll start off with things. The maybe original motivation for people thinking about the Riemann hypothesis was that if you assume the Riemann hypothesis, you get all these fantastic consequences for the distribution of prime numbers. And so one consequence is that if you assume the Riemann hypothesis, then you get a nice understanding and asymptotic formula for the number of primes in short intervals. So if maybe I'm interested in the question of how many primes are there between x and x plus y, well, if the primes of size x, then we expect primes to occur with density roughly 1 over log x. The length of this interval is y, so you might guess that the number of primes in the short interval should be roughly y over log x, at least when y is smaller than or equal to x. And that's not going to be precisely true, so maybe there'll be a small error term. But if you assume the Riemann hypothesis, you can prove that this guess is indeed correct if y is a little bit bigger than x to 1/2. So maybe if y is bigger than x to the half plus epsilon, and x is sufficiently large in terms of epsilon. And so this is one consequence of the Riemann hypothesis, a good understanding of primes in short intervals. It's a very old conjecture of Legendre that there should always be a prime between any two consecutive squares. And this falls just short of proving Legendre's conjecture. If you are able to take y to be maybe x to 1/2 over 2 or something, then you'd be able to show that at least for all sufficiently large squares, there's a prime between any two consecutive squares. Okay, so this is, if you assume a big conjecture, then you get nice consequences for primes in short intervals. But maybe the slightly disappointing thing about this is that I don't know how to prove the Riemann hypothesis. And so I'm therefore a little bit stuck. But you might hope that if all you care about was something like this to do with prime numbers, then you wouldn't actually need an assumption which is quite as strong as the Riemann hypothesis. And it turns out for this particular problem, that is true. So the Riemann hypothesis says all non-trivial zeros of the Riemann zeta function lie on the line real part of s equals 1/2. And from the point of view of this question, a sufficient substitute is to show that most zeros of the Riemann zeta function lie close to the line real part of s equals 1/2. So maybe I'll make that a little bit more concrete. We can draw a picture of the complex plane where I have the real part of s on the x-axis, the imaginary part of s on the y-axis. We know that all zeros of the Riemann zeta function have real part between 0 and 1. We believe that they should all lie on the line real part equals 1/2. And to measure or to count how many zeros are far away, I can think about counting the number of zeros in some box. So I'm thinking about the imaginary part going up to t, and the real part being bigger than some parameter sigma. And I can think about the number of zeros in some box, which is what I'll call n of sigma t. So the number of zeros of the Riemann zeta function such that the imaginary part of the zero is at most t, and the real part of the zero is at least sigma. And so the Riemann hypothesis is just the claim that n of sigma t is equal to 0 whenever sigma is bigger than 1/2. But it turns out that if you can show that n of sigma t is sufficiently small, then you can get consequences like this. And so one fairly simple to prove lemma is the following. Let A be a positive constant such that n of sigma t is bounded above by t to the power a, and maybe I'll allow some small quantity going to 0, times 1 minus sigma. So I'm assuming this for all values of t and all values of sigma. So if you have a bound like this, then you get that the number of primes in the short interval x up to x plus y is equal to what you expect, which is roughly y over log x, provided y is not too small. And here the quantification is that y has to be a little bit bigger than x to the power 1 minus 1 over a. So we know that there's just slightly more than t zeros of the Riemann zeta function on the line real part of s equals 1/2. And so for this to hold for all values of sigma and t, in particular for sigma equals 1/2, the best possible constant a you could possibly have would be a equals 2. And we see that if we take a equals 2, then we get x to 1/2 plus epsilon here. And so we get something that's almost as strong as the Riemann hypothesis from the point of view of counting primes in short intervals. But all we needed was a weaker bound that n of sigma t is bounded essentially by t to the power 2 minus 2 sigma. And so the conjecture that you can take a equals 2 is known as the density hypothesis. And this would be in various different contexts, but certainly for this question about asymptotics for primes in short intervals, almost a possible substitute for the Riemann hypothesis. Now, the hope, of course, would be that therefore maybe you could prove the density hypothesis even if you're unable to prove the Riemann hypothesis. The problem is that I don't know how to prove the density hypothesis, and so I'm also stuck. However, the key point is that although I can't prove the density hypothesis, we can unconditionally prove bounds of this shape for slightly bigger constants a, and therefore we can unconditionally get results about primes in short intervals using this method. Results. And so in particular, I'd like to mention two important bounds. So there's a result of Ingham from 1940 that says that n of sigma t is bounded above by t to the power 3 times 1 minus sigma over 2 minus sigma plus a small quantity. And then there's a result of Huxley from 1972, so just over 30 years later, that proves n of sigma t is bounded above by t to the power 3 times 1 minus sigma over 3 sigma minus 1. plus little o1. And okay, it takes a little bit of digesting what these quantities are, but if you look at the exponents, you find out that Huxley's exponent is smaller when sigma is bigger than or equal to 3/4, and Ingham's exponent is smaller when sigma is less than or equal to 3/4. So this is best for sigma less than or equal to 3/4, and this is best for sigma greater than or equal to 3/4, and at 3/4 they both give the same bounds. And if you just put both of these together, they imply that n of sigma t is bounded above by t to the power 12/5 times 1 minus sigma, and maybe I'm going to ignore little o 1 factors, and a fairly immediate consequence, at least if you're a little bit careful about issues to do with sigma being very close to 1, shows that the number of primes in a short interval x up to x plus y is exactly what you expect. If y is a bit bigger than x to the 7/12. But it also shows a little bit more than that you could improve this constant 12/5 if you were away from the point when sigma equals 3/4, where these two bounds overlap. So if you had some completely separate argument that somehow showed there were very few zeros of the Riemann zeta function with real part close to 3/4, of course we expect there to be none, then you would improve this constant 12/5 at least slightly, and you get a better result about primes in short intervals. I guess I should mention that if you don't worry too much about the low order terms and the little o1s, Ingham's result has essentially not been improved at all since he proved it in 1940. So this is still essentially the state of the art for sigma less than or equal to 3/4, whereas there's various different arguments that improve quantitatively on Huxley's bound in various different regimes, important work of Utila, Heath Brown, Bourgain, and many others. But nothing's been improved for sigma less than or equal to 3/4. Okay, so how might you try and prove any result like this? Well, the proofs, and how does this relate to my title of large values of Dirichlet polynomials? The proof of these results relies on studying Dirichlet polynomials. So what is that and how does this relate? Well, there's this method known as the zero detection method, which essentially says that n of sigma t can be bounded above by, maybe I'll write it in this way, something that looks like the density hypothesis, so would be a great bound, plus some other term, which is the supremum over all quantities n, which are a little bit less than t to the 1/2. Maybe I'll put a lower bound here as well, just to make things easy, and complex sequences an bounded above by 1 of some quantity r, which will depend on n sigma in t, where r is the maximal size of a one-separated set of points matrix size, a one-separated set, let's call this set W, such that if I look at the sum an n to the power it, summed between little n is big N and 2 big N, this I'm assuming is taking values of size n to the sigma. So we call these finite sums of the form some coefficient an times n to the it, a Dirichlet polynomial, and r is counting the number of times this Dirichlet polynomial takes a large value in the interval 0 up to 2. And so if you could show that Dirichlet polynomials rarely took large values, then you would show that the set W is small, so R is small, and then you'd have a good bound for n of sigma t, and you'd show that there's few zeros of the Riemann zeta function lying in that box. Just that the complex number is bounded above by 1. And so maybe the key question in this area is what is the best bound for R in terms of n, sigma, and t. And the conjectured answer is given by Montgomery, that it's believed that R should be bounded above by essentially n to the power 2 minus 2 sigma for sigma whenever sigma is a fixed number bigger than 1/2. So unfortunately, we don't know how to prove Montgomery's conjecture, but we can prove some partial bounds in that direction. And there's two particularly important bounds that I'd like to mention. So one is the mean value theorem for Dirichlet polynomials. And this says that R is bounded above by, maybe I'll not worry too much about t to the little o1 factors, but t to power t times n to the power 1 minus 2 sigma plus n to the power 2 minus 2 sigma. And then there's the so-called large values estimate, based fundamentally on work of Montgomery and Halash, and then with some refinements due to Huxley, which says that R is bounded above by t times n to the power 4 minus 6 sigma plus n to the power 2 minus 2 sigma. And so if you look at these two bounds, you see that this exponent 4 minus 6 sigma is smaller than 1 minus 2 sigma whenever sigma is bigger than 3/4. And so this gives a better bound when sigma is bigger than 3/4. This gives a better bound when sigma is less than or equal to 3/4. And it may be, therefore, it's not super surprising that Ingham's result essentially is a consequence of the mean value theorem for Dirichlet polynomials, and Huxley's result is a consequence of the large values estimate for Dirichlet polynomials. I guess maybe these results combined with the observation that if I take a power of a Dirichlet polynomial, that also essentially has the form of a Dirichlet polynomial. And so it's these sort of large values estimates and mean value theorems that are the key to these results on the number of zeros of the Riemann zeta function and counterexamples to the Riemann hypothesis. So the main result that I'm going to talk about today is work with Larry Guth, and this is a bound that does better than the mean value theorem and the large values estimate, at least for certain ranges of parameters. So our result is that R is bounded above by t to the little o1 of n to the power 2 minus 2 sigma. Then there's a n to the 18/5 minus 4 sigma, and then there's a t times n to the 12/5 minus 4 sigma. And if you do a little bit of algebra comparing this and these two results, You could maybe convince yourself that this does better if sigma is less than 8/10 and bigger than 7/10, and n is less than equal to e to the power 5/6.
Sorry, both of those are -4 sigma?
They're both -4 sigma, yes. Yeah, maybe my handwriting's not too good. Thanks. And so the key point here is that the range of sigma that we're looking at includes sigma equals 3/4, which we saw from before was the critical case. Jeff?
Just want to go back and understand the definition of a bar.
Yeah.
W.
So
W related to.
W is a set of one separated points in 0 up to t of maximal size, and R is just the size of W.
So maybe for all lowercase t in W.
Yeah, sorry. Thank you. So W is a set where this Dirichlet polynomial takes large values that is one separated, and I want to take a set which has maximal size, and R is just the size of that set. Does that make sense? Great. Yeah, maybe actually this is an actual place to pause. Are there any other questions about what the statement of our result is? So the number of terms in the sum is capital N, and R depends on capital N, but for at least for the point of view bound in n of sigma t, we're only looking at n going up to t to the power 1/2. But R, in principle, has n as a input parameter, and so we're expecting a bound on R that's going to depend on n. Any, yeah?
Why does this change happen in 3/4?
I don't have a terribly good sort of intuitive first principles argument for this, that we essentially have, we know that understanding exceptions to the Riemann hypothesis can be reinterpreted as bounds for large values of Dirichlet polynomials. We have these sort of two techniques that we have. One of them works pretty well if you're looking at not too big large values. One of them works very well if you're looking at very big large values. And so this is very strong when sigma is very close to 1, whereas this is sort of pretty strong when sigma is close to 1/2. And then there's going to be some point when they both give the same bound. And so that's going to be some point between 1/2 and 1. And it just so happens that it's at the midpoint at 3/4. Any further questions?
Just a very quick one. So back to this definition.
Yep.
I want to make sure I'm seeing the exponent correctly. So we have supremum of R. So is it ends between t to the 1/10 and t to the what?
That's t to the power 1/100, but it doesn't really matter too much. So the lower bound is unimportant, but yeah, I agree that that 1/100 is not written terribly clearly. Any extra questions? Okay, so hopefully we're all happy with the definition of R. The key problem that we're trying to bound the number of these large values, we have these two basic estimates, and I'm claiming an improved estimate that improves things essentially when sigma is between 0.7 and 0.8, which in particular includes the case when sigma equals 3/4, which is what we had in mind as our critical situation before.
Seems that this conjecture of Montgomery would imply that the second term is negligible compared to the first, but in all of your bounds there, the second term is large.
Yeah, so Montgomery's conjecture says that you should have this n to the 2 - 2 sigma type term for all values of n. These imply that if n is very large, maybe bigger than t, but Montgomery says that that should hold even when n is smaller, when in practice these two terms are the key dominating ones.
By square root of t, so that would only be t to the 1 - minus sigma, not t to the 2 minus 2 sigma, which is the leading term.
Yes, so Montgomery's conjecture would be given exceptionally good bounds for this, and so this would be the somehow dominating behavior, which has slightly different behavior. It's slightly different to just large values of Dirichlet polynomials. But from the point of view of bounding at n of sigma t, you wouldn't need something quite as strong as Montgomery's conjecture. Okay? So maybe I'll go on, and it's maybe not too surprising that if you then put this bound for R into the n of sigma t bounds, and you combine it with some of the pre-existing estimates, you get some immediate consequences. That one consequence is that n of sigma t can be bounded above by t to the power 30 minus 30 over 13 times 1 minus sigma, it's low 1. And 30 over 13 is smaller than 12 over 5. So we've improved this zero density estimate. And as a consequence, we get an improved result for the range when we get an asymptotic for primes in short intervals. So we now can go down to 17 over 30, but maybe slightly less interesting than the totally precise numerics is the fact that we're getting the first improvements on Ingham's bound in the region when sigma is less than or equal to 3/4 that we've been stuck on for 80 years. Yeah. So just to recap, to understand, to count bad zeros that are counterexamples to the Riemann hypothesis, we want to bound n of sigma t. There's a well-established methodology to turn this into bounding large values of Dirichlet polynomials. There are two classic results, and then various more complicated refinements in other regimes. And we're claiming an improved bound for large values of Dirichlet polynomials, which as a consequence improves these bounds on zero density estimates. Okay, so with that established, I'd like to spend a little bit of time given a sort of proof of principle, sketching some of the ideas that go into the proof.
Maybe you could say one word, again, point out this some version of that conjecture and I guess you're going to get into decoupling.
So today we're not going to get into decoupling okay, yeah, I can't actually remember the precise formulation of Bourgain's kind of observation that this is an exceptionally strong and deep conjecture of Montgomery, I think is the fair summary, and this would have pretty wide implications, and in particular is connected to issues to do with the Kakea problem. And no, not directly at all. Okay. So to give a hint of the methods, I'd like to focus for today on just a very specific situation where we can hope to get just a small proof of principle result that goes beyond what was known before. So today, I'd like to think about just the case when sigma is equal to 3/4, which we knew was the critical case. And I want to think of the parameter n of being of size t to the power 1 minus delta. So in this zero density setup, we're only interested in n going up to t to the 1/2, but you can always square a Dirichlet polynomial, and so think of ones of size close to t. And it turns out that this, getting an improvement in this regime, essentially alongside the subdivision trick, will give an improvement in general. So this is going to be a key critical situation, and it's a little bit easier to see what's going on when n is of size very close to 2. And so in this situation, we have our set W, which I'm going to imagine is a well-separated set. And I'll imagine it's in 0 up to t, although the same proof works for any interval of length t. And we're going to imagine we've got some fixed sequence an. So an n to the power it is bigger than or equal to n to the sigma for all t in W, and we want to beat the size of W, which in this case is R, an upper bound of t times n to the minus 1/2, which is what both the large values estimate and the mean value theorem will give in this context. Yeah, t to the epsilon separated is maybe not too important, but I'm assuming a little bit better separation, but it kind of, if I have a bit of better separation, I get the same sort of bounds just with a t to the epsilon loss, which would be negligible. Okay. So the first step will be algebra. So let M be the size of W by n matrix with entries just given by n to the it for n between n and 2n and t and W. So this is a matrix, and note that if I apply this matrix to the vector A of coefficients, then this is just the value of my Dirichlet polynomial if I'm looking at the tth component of that. And so in particular, I have that n to the 2 sigma, which is n to the 3/2, times the size of W is bounded above by the sum over all points in W of the second moment of this Dirichlet polynomial. Which is then just equal to the this vector the square of the L2 norm of the vector M of A. And since A is one-bounded, this is just bounded above by the matrix norm of M squared times N. And so to get a good bound on the size of the set W, it's sufficient to just get a good bound on the matrix norm of this matrix M with entries n to the it. So how might one do that? Well, the matrix norm is equal to the largest singular value of this rectangular matrix M, and this is equal to the square root of the largest eigenvalue of M times M conjugate transpose. And so here I just have a rectangular matrix with non-negative eigenvalues, and I want to bound the largest eigenvalue. So it's a simple spectral problem, and one easy bound would be to say that the kth power of this largest singular value is just bounded above by a suitable power of the trace. So the trace of m star to the power k is the sum of all the eigenvalues to the power k, And so if I take the 1/2kth power of that, this has just given me the largest eigenvalue plus some extra terms that are all non-negative. So unfortunately, when k is small, you're losing a lot by looking at all the possible eigenvalues rather than just the biggest one. And so this doesn't give terribly good bounds. When k is large, in principle, this should give very good bounds, but it turns out this is quite difficult to handle and I don't really know how to get good estimates. But by being a bit more careful, we can do a modified version of the case when k equals 3, and essentially, lying slightly here, I can bound this above by the trace of m star cubed minus the trace of m star cubed over n squared, all the power 1/2. And by being able to subtract out this term, I sort of regularize the term from there being lots and lots of eigenvalues of essentially the same size, and so it just suffices to bound this quantity. So what does all of this give us once we've done the linear algebra? And what does this cubic trace look like? It means it suffices to bound a sum that looks like this cubic trace. So I'll have, expanding everything out, I'm going to have 3 points in W, and I'll have n1 into n3 of size n, and then I'll have n1 to the power I t1 minus t2, n2 to the power I t2 minus t3, and n3 to the power I t3 minus t1. So in principle, you might hope to get better results with the fifth power. I just don't know how to handle the fifth power. Yeah, exactly. So, but essentially, it becomes a harder problem as k gets larger. So if you're looking only at k equals 1 or 2, essentially, you can't, even optimal bounds for the trace would not give you any non-trivial improvement when sigma equals 3/4. K equals 2 is morally very closely related to the Halash large values estimate. And so you need to look at k being bigger than 2, but it gets quite a lot harder as k gets bigger. And so k equals 3 is the next easiest case where we're able to say something non-trivial. And so this is the sum that we're interested in. And if you work through what the algebra is in this particular situation, you want to beat the bound t cubed. So if I can show that s is a bit smaller than t cubed, then in principle I'm improving on all the previous estimates. And so this is the key situation that I want to focus on. Okay, so if you look at a sum like this, you have these fairly long sums over integers n1 and n2 and n3, and so the natural inclination from anyone is to apply the approximate functional equation. Also, a different way of thinking about that would be Poisson summation and then stationary phase to turn these long sums into shorter sums. Unfortunately, this turns out to be not a terribly good move, because you then get factors involved in these exponents, t1 minus t2, t2 minus t3, and t3 minus t1, which link the variables t1, t2, and t3. And if you can't unlink the variables t1 and t2 and t3, then it's going to be very difficult to get any cancellation in this sum over t1, t2, t3. And even if you had square root cancellation in everything else, you'd be getting a bound of the size of w cubed times n to the power 3/2. But in the critical situation, when w is t times n to the minus 1/2, here, that would be giving us a bound of precisely t cubed, and we wouldn't be getting anything at all if we just had square root cancellation in the n variables. And so we need to do something which is a little bit better than that. So what do you do if you're not going to apply the approximate functional equation? Well, maybe the first key idea is that you do want to apply approximate summation, but you don't want to apply stationary phase to simplify the resulting Fourier integrals. So just check where I am in my notes. Step 2, Fourier analysis. So if you apply Poisson summation, but no stationary phase, you get that the sum is roughly equal to n cubed times the sum over m1, m2, m3 of size t over n, which is the dual sum. You still have your sum of t1, t2, t3 in w, and then you have an integral of let me just check where I am. u1 over u2 to the I t1, u2 over u3 to the I t2, u3 over u1 to the I t3 du, and I've forgotten a factor of e to the 2 pi I m dot u. And this integral is maybe over something like an interval of length 1 cubed. So there's a bit of a gambit involved in not applying stationary phase. If you applied stationary phase, you would simplify these integrals and you'd win a factor of t to the power 3/2 here. So we've given up a factor of t to the power 3/2 by not applying stationary phase. But one thing that we're gaining is that the t1, t2, t3 variables are nicely separated from one another. And so in particular, we can hope for good cancellation over the sums t1, t2, t3. So this is equal to n cubed times the sum over m of size t over n, and then there'll be an integral of r of u1 over u2, r of u2 over u3, and r of u3 over u1, e of m dot u du, where r of x is equal to the sum of x dit for t and w. And so this is making use of this separation of variables which have a nice shape. Now, unfortunately, this looks like a pretty bad gambit, that even if you had square root cancellation in all of these R functions, you might hope to win a factor of w to the power 3/2, but we've lost the factor of t to the power 3/2, and so this is a net loss for us. And so to make any progress, it's not sufficient to just have cancellation in the R functions. You need to get some simultaneous cancellation in the R functions and this integral over u, because without that, you're not going to get any progress at all. And so maybe the first key observation is therefore we don't want to apply stationary phase, but then the second key observation, which allows us to have a hope of this given something non-trivial, is a way of trying to get this simultaneous cancellation, and that's to just note that the arguments of the R functions lie in a two-dimensional subvariety because the product of the arguments is always equal to 1. So step 3. I'm going to change variables. So because the product of the arguments is equal to 1, we can let vi be ui over u3 for I equals 1 and 2, and we get then sum of n cubed m of size t over n, an integral of r of maybe r of v1, r of v2 over v1, and r of 1 over v2, if I've done the algebra correctly, and then an integral of e of n m1 v1, maybe I like this down here, a integral of e to the power 2 pi I, which is my e function of n times m1 v1 plus m2 v2 plus m3 of u3 du3. And then there's a dv1, dv2. And the key point is that this inner integral over u3 is going to have a huge amount of cancellation and essentially be equal to 0 unless this argument is essentially equal to 0. So the inner integral is approximately equal to 0 unless m1 v1 plus m2 v2 plus m3 is approximately equal to 0. And moreover, this allows us to win back a factor of 1 over t. And so we'd had this gambit where we'd given up a factor of t to the 3/2. Now we've won back a factor of t, so we've only really given up a factor of t to 1/2, and we have nice separation of the variables in our R functions. And so the key point here is we win back a factor of t, and we're left with n cubed over t times the sum over m of size t over n, and then some integral of r of v1, r of v2 over v1, and r of 1 over v2 dv1, where we're integrating over the line m1 v1 plus m2 v2 plus m3 is equal to 0. And now, if we did have square root cancellation uniformly everywhere for these R functions, we would win an extra factor of w to the power 3 over 2, and this would allow us to comfortably beat t cubed in the situation that we're looking at, and we get a big win. So we're now in a situation where we hope that we might be able to get a non-trivial bound. Maybe I'll stick with these middle boards. So we would get a bound then if we're getting square root cancellation of the R function absolutely everywhere, but the R function is defined in terms of this set W that I don't know anything much about at all, and so I can't possibly hope for uniform square root cancellation. But I might hope for something on average, which would be an adequate substitute. So maybe step 4 is you're interested in the R function itself. And I'll call this R function plus low energy. And you can just do some basic estimates on the R function. So you could look like at an L2 moment, and this would say that the R function is typically of size square root. So you would be saving a factor of w to the 1/2 average. Yeah, and okay, I guess I should point out that this is pretty bad notation, that my R function here is totally unrelated to the quantity R. So R of x is the sum over t in this set W of x to the power it. And if I look at an L4 moment, this is essentially the additive energy of W to the 1/4. So what's this additive energy? Here, E of W is the set of points T1, T2, T3, T4 in W such that T1 plus T2 is equal to T3 plus T4, maybe with an error term of size 1. And a simple Cauchy-Schwarz bound would show that, would then imply that the sum that we're interested in is bounded above by T squared W to the 1/2 times the additive energy of W to 1/2. And so in particular, if there's few quadruples that sum these pairs, you get a very strong bound for S, and you get a good bound improving all your large values estimates for Dirichlet polynomials. And when you work out what this gives, this gives a good bound unless the energy E of W is bigger than W cubed times T to the minus 2 delta. But so if I remember, delta is this parameter coming from the fact that I'm assuming that P is n to the power 1 plus delta. So we're thinking of delta as some fixed constant that's very small. And for E of W, a trivial bound for E of W is essentially W cubed, because I can just choose T1, T2, T3, and then T4 is essentially uniquely determined because W is well separated. And so this is saying that when delta is small, I'm in a good situation and I get improvements on everything, unless the set W has very large additive energy that's almost as large as it can possibly be. And you might hope that when the additive energy of the set W is very large, then W must have a certain amount of structure to it, and then you might be able to exploit that structure in some way. So we need a complementary bound when the energy is large, but maybe the key contribution in our work is handling this generic low energy case. So maybe step 5 is going to be high energy. And the key contribution here is a pre-existing bound of Heath-Brown on Dirichlet bounds for Dirichlet polynomials over different sets. So there's a bound of Heath-Brown. I can't remember exactly when, but maybe it's around 1980. Who shows that if I'm summing over T1, T2 in some set W, and I'm looking at some Dirichlet polynomial, with one bounded coefficients, and I'm looking at it evaluated at the difference T1 minus T2. So it's important that I'm looking at the difference, and it's the T1 and T2 arranging over all points in the same set. Then I get a bound which is almost optimal. So the optimal bound would be Wm squared plus W squared m, and he gets precisely this with some other term that's, for our purposes, reasonably small, and so I'm not going to write that down. It's essentially an almost sharp bound over these different sets, at least provided m and w aren't too small, which is what's captured in this term. And an immediate consequence of this is that you can essentially assume that the additive energy of a set W coming from our Dirichlet polynomial is smaller than W cubed T to the minus delta. So that's just applying a very simple consequence of Heath-Brown's work, working a tiny bit harder. Means that you can actually handle the situation whenever you're good if E of W is larger than W cubed t to the minus 2 delta. So this almost completes the picture that we're good if E of W is sufficiently small compared to W cubed t to the minus 2 delta, and we're good if E of W is sufficiently large compared to W cubed t to the minus 2 delta. But there's one intermediate value of E of W where we currently haven't handled anything. And so this is the final step where we use affine averages we go back to the sum S that we're interested in. Maybe I've erased it now, which is a little bit unfortunate. And we had this sum over M1, M2, M3, all of size T over N. And this bound followed from just treating each M term exactly the same and not using this averaging over M. But it turns out that if you analyze when this would be sharp, the previous bound would only be sharp if and only if there exists a small set U, which is when the R function would be taking large values, such that for most U in U and most M1, M2, M3 of size T over N, we have that M1U plus M2 over M3 is also in U. So U would have to be approximately closed under these affine transformations, these affine averages. And so we show that actually any small set U can't be approximately closed under these affine averages. And that allows us to win an extra factor of this averaging, which is of size T to the delta. And then when we put that into our original bound, this refines the low energy bound and handles everything except when E of W is bigger than or equal to W cubed, essentially. And so E of W would have to be really very close to the absolute maximal size, and we know that can't be the case from the Heath-bound results. And so then, once you put everything in principle, you've improved on the critical situation on all our previous estimates. And then it requires a little bit of extra numerical work to check how this behaves in for different values of sigma. And when you choose your parameters n and t and everything optimally, you get the large values estimate that I wrote on the board with Larry. So I think I'm more or less out of time, so maybe I'll stop here. Thanks a lot for listening. I hope you enjoyed the talk.
Thank you, James. Questions? Go ahead.
So for the benefit of those of us trying to learn various techniques, could you say a few words about what stationary phase means and how it's useful in estimating sums like this?
Yeah, sure. So stationary phase is a technique in harmonic analysis. So the typical situation you're interested in is some integral, which is an oscillatory integral. So you're looking at e to the power 2 pi I f of x dx maybe, where I'm thinking of f as some smooth function. Maybe I have some extra smooth weighting or something. And if f is typically taking large values, then this e to the 2 pi I f of x will be oscillating very, very quickly. And so we'd expect there to be lots and lots of cancellation because you're going around the unit circle many, many times. However, if x is a point when the derivative of x vanishes, then suddenly this points, this exponential suddenly becomes stationary and you're not oscillating. And stationary phase is a way of estimating these integrals, which is essentially saying that the dominant contribution from these integrals is coming from those critical points x when the derivative vanishes and the neighborhood around them. And so it's a general method for getting good bounds on these oscillatory integrals just by analyzing the critical points of the function f. And so it allows you to simplify these oscillatory integrals into something concrete just in terms of the points when the derivative vanishes.
Following up on these questions, did you stationary phase early on?
Yeah.
When you did this, so you were careful to say, I won't do that.
Yeah.
You get sums that would be quite explicit. Would you go back to where you started, or would you get something that's, I mean, you still have to be able to get in the same position eventually, because you're not losing by using stationary phase.
So the whole point is that these, so I can apply stationary phase, and if you say that's an identity, so I haven't lost anything I say, but the shifts of my sums in this annoying form because the variables aren't separated. So I would conjecture that you would get really good cancellation on these sums, but the coefficients coming from the fraction, I just don't know how to handle it. And so I'm happy to pay a price to get my sums into a nicer form, but essentially the only thing I know how to do is to unwind the stationary phase to be able to get a handle on these things.
First, so you sort of zoomed in on 3/4 as the critical place. Now we have two critical places, I guess, 7/10 and 8/10. And do you have any thoughts on?
So it turns out that 7/10 is the one critical place if all you care about is, say, primes and short intervals or zero density estimates. So yeah, as there was before, you can now write down a very explicit worst case scenario for a very particular length of your sum n, a very particular size of the additive energy of the set W, and you can write down all these parameters, and it's that specific situation that one would need to handle, and that corresponds to sigma being 7/10. At sigma equals 7/10, currently lots of our estimates look quite difficult to improve. We're exploiting these affine averages, but the bound we get, at least in this formulation of the problem, is essentially sharp for those affine averages. We're getting a bound on the additive energy of the set W, but in the critical case when sigma equals 7/10 and all the parameters at the worst point, our bound for the additive energy is essentially sharp as well. So there's various different ways in which I don't know how to improve any stage of the arguments at 7/10. But it is the case that just as in previous works, I can write down a very explicit set of parameters, and if you can improve the situation just for that explicit set of parameters, then you'll be able to improve the overall results. Yep.
Besides primes and short intervals?
So I expect there to be a number of related results through the prime numbers, which have similar limitations, and you might hope that our methods would apply in a similar way there. So certainly, if you're looking for asymptotics of primes in almost all short intervals, this gives an improvement. If you're just looking for the upper bound on the largest possible gap between primes, the current record is Baker, Harman, Pintz. But again, their work was limited essentially to do with estimates at sigma equals 3/4 for Dirichlet polynomials, and so our work should improve on the largest upper bound for gap between primes, or almost always short intervals almost always containing a prime. If you're looking for a fixed modulus Q, then you can look at the same sorts of questions where instead you're looking at Dirichlet polynomials with Dirichlet characters mod Q. For a fixed Q, I think we should get some somewhat similar improvements, but our methods at the moment would give slightly weaker results in general. But that would correspondingly have consequences for primes and arithmetic progressions, say the largest modulus Q when you're getting an asymptotic for primes in an arithmetic progression mod Q, provided you don't have any z equals 0 or 0 very close to the 1 line. So there should be various other consequences. at the moment, all the consequences I know are somewhat related to short interval arithmetic progression type situations, but there's quite possibly other things as well, which I haven't thought through yet.
What about error in prime number theorem?
No, so the error term in the prime number theorem is fundamentally dominated by the worst possible individual zero. And so the error term in the prime number theorem is really all a question about zeros as close to the one line as possible. So this will only ever possibly be useful if you're looking at questions which are fundamentally about there not being too many zeros that are counterexamples to the Riemann hypothesis. But we're not getting any improvement on the zero-free region, and so we're not getting any direct improvement on the error term in the prime number theorem. For that, it's the really bad zeros very close to the one line rather than things to do with the three-quarter line that are critical.
Give you better zero density.
Yeah, so we get at least if you care about the zero density bound of the form, n sigma t to the power t to the power 1 minus sigma times some constant a, we're improving that constant a where the previous record was 12 over 5 to 30 over 13. And 30 over 13 is a little bit smaller, so we've gone from 2.4 to a number that's close to 2.3. So you get an improvement on zero density bounds, and if you care about the explicit dependence on A on sigma, you can get a more explicit thing that does better in, whenever sigma is away from 7/10, because 7/10 is the critical situation.
In the first step of your proof, you introduced a matrix and you said that your goal was to bound its operator on. So what is the bound that you get at the end? Because I got lost in for the steps.
That's a that's a good question. I'm not sure I can even do the algebra in my head right now because yeah, so we wanted to bound the largest singular value of the matrix by something which was a bit smaller than t to the 1/2, and I've sketched an argument that will get you some very small improvement on t to the 1/2. If you go through and actually quantify everything, then I get a concrete improvement over t to the 1/2 in terms of what the value of sigma is and various other things. But off the top of my head, I can't write down the expression you get, but it's not too difficult to unwind from our basic statement about large values estimates what the bound for the largest eigenvalue of this matrix is. But I can't do the algebra in my head on the board.
You mentioned that like three was like the sort of the first number that sort of gives something non-trivial, and that 5 was sort of like way out. But like if you could handle like larger numbers, I guess would you be able to extend Ingham's result all the way to 1/2?
Yeah, so I mean, essentially, if there's a natural conjecture on what the trace should be for the pth power of the trace, and if you plug that in and you assume that for all sufficiently large values of k, not only would you improve Ingham in the full range, you'd actually be proving Montgomery's conjecture. And so that's really relying on having sharp bounds for k being very large. But in principle, if you had sharp bounds for smaller values of k, you would get improvements in bigger and bigger regions. And morally, yeah, as k goes up, you should be able to get improvements further and further towards the line 1/2, provided you're able to handle the trace in a sharp manner, but I don't know how to do that at all.
So there is a conjecture on the singular
value of that matrix, which is equivalent to Montgomery conjecture.
Yes. Yes.
Okay, this conjecture.
The conjecture on the largest singular value. So I think Montgomery's conjecture is essentially okay. I may be making a mistake, but if I've got the algebra right in my head, it would be would be saying that the largest singular value should be bounded above by t to the little o1 n to the power 1/2. And the trivial bounds would be bounding the largest singular value by t to the power 1/2. And we're getting something that is in between n to the 1/2 and t to the 1/2.
So just a question of a speculation. So yeah, when you mentioned that when k equals to 3, then the energy, additive energy comes to the picture. Is it possible that when you go to the larger case, then higher Gauer's norm can be useful?
So unfortunately not that when you look at higher values of k, so a natural thing to do is to say, okay, we get some fairly decent results when k equals 3. What about when k equals 4? You can try and run exactly the same argument. Instead of having a 3-dimensional Fourier integral, you'd have a 4-dimensional Fourier integral. You can play the same trick that you have a codimension 1 subvariety, and so you have a 1-dimensional integral that you can handle very nicely. And then rather than having a 1-dimensional integral of 3 copies of the R function, you'd have a 2-dimensional integral of 4 copies of the R function. And so if anything, it looks like a lower moment problem rather than a higher moment problem, which you might hope works in your favor. But you still paid this big price of not applying stationary phase. And so you paid a much bigger price when you've given it up for this 2-dimensional integral. And so to get something that's better than what we get when k equals 3, you need to somehow exploit simultaneous cancellation between the U integration and these 4 copies of the R function, which I don't know how to do at all. You could apply stationary phase, but then you've broken all the structure in your sets. And so it looks like a mess, like where you started off with.
Okay, so I think that's